My name is Artemy. I work at JetBrains as a head of C, C++ ecosystem, whatever this means. Basically, you can think of me as a product lead, whatever. And first, before we start presentation, product leads, product managers, they ask questions to know the audience. So first of all, very simple question, folks. Please raise your hands who are C++ developers. Okay, the majority, except for JetBrains folks. Okay. Please keep them up. So now, who of you are using C++ 11 and higher? Okay. C++ 17? Okay. C++ 20? Okay. C++ 23? I see some strong guys here. Thanks so much. Why I'm asking this? So basically, because we are going to talk about const expression, and it has some stages. It's been evolving since C++ 11 and in other versions as well. And before we jump to the talk, so this is the agenda. From the schedule, you might think it will take an hour and 10 minutes, and I have this timer here. It won't take an hour and 10 minutes, don't worry. It will take a maximum 40 minutes, so we will have a good time to have late dinner, to talk, and so on. We will talk about some the problem statement. I will show some demos, examples. I will show how actually in CLion you can debug const expressions, how it works under the hood, and then questions and so on. Let's jump into it then. So constexpr has grown up. In C++ 11, you can use just single return statements as a const expression. Very simple, nothing super complex. In C++ 14, you can start having loops, variables, branches, and so on. So the programs that are written under the const expression become harder and harder. Next, in C++ 17, you have the if constexpr, you have lambda support, and so on. C++ 20 goes even further. Now we have dynamic memory allocations, and the programs that we can write in C++ 20 under the const expression are much harder. C++ 23 brings us a unique PTR and even more standard libraries constructions for this. And in C++ 26, I guess the plan is to have exceptions as well. Now, let's talk about the complexity of debugging it. So, in C++ 11, you basically can look at the expression and get the understanding. It's pretty easy, right? No debugging needed. In C++ 14, might be harder. In C++ 17, similar hardness, but yeah. C++ 20, okay, we have dynamic memory allocations. It's getting harder and harder. C++ 26, and God knows what's next, right? So, raise the hands who has written more than one-liner const expressions? Okay, good. So we have some brave folks here. So in C++ 11, it looks like this, right? You square to a variable, and then that's it. In C++ 26, this is something you can write. And the complexity grows and grows and grows. You can invoke functions and so on. And to be honest, we've been there. I feel you. It's hard, and you always get some errors here and there. And so, how do you do it now? How do you debug const expressions now? Let me open the CLion here. No, we don't want to restart it. Definitely not now. I think you've all had this exercise somewhere in your life, probably when joining a new company. Binary search, you all know the issues there, you all know the bugs you have had, and maybe if you're lucky, you never made a mistake on the interview with binary searches. So we see some errors, right? We see that CLion gives us help that this is not going to work out here. Some issues there, and there is a bug. I know it. I wrote it. And how do you debug it now? Like what I've seen people do is copy this, comment this, put it here, and then just for the sake of remove context expression. Then you put the debugger point, and then you basically start debugging. And that's it, right? You debug, you go through variables, oh, we missed the point. So that's how it goes right now mostly, in most cases. At least from what we know about C++ developers, that's the #1 tool to debug const expression, to unconst express it. So not the best idea for the various reasons. So that's the first approach. Just remove const expression, debug at runtime, and the issue is behavior might be different. And the complexity of functions getting harder and harder. And then if you have a lot of call chains and so on, it's a nightmare. Second, cout doesn't work there. It doesn't work. It's not allowed in const expression. And my favorite one, the third one, do you know? Stare harder. Look at it. Look at the problem. And you see it, right? Well, it probably will work in the binary search. You've all done this. But if it's just a bit harder, no way. So the question is, if only we could debug it properly. This is CLion, which version is it? 25.2, something that was initially released in summer last year. And that's how you do it, how you debug in the old CLion. And the new CLion, okay, we don't want to restart it right now, don't worry. You have this beautiful bug here. So and it says that you can start debugging evaluation. Interesting, right? So we know that there's an issue somewhere in this. Let's debug with this data. Okay. So we can debug something that runs in constant expression. And this is your regular debugger interface that you have in any other IDE that you are so attached to. You can jump through standard library calls because we call data on the array. Then we call size on the array. Then we go inside the binary search function, binary search call here. And as you can see, we can debug it, as we do debug every other function. You can see the values of your variables here. You can see the evaluations of templates here, the type names, and so on. And you can actually go and debug it properly. And you know what's cool? So in previous example, we overshoot the debugging phase. What we did is like this. And then oh, it's we overshoot. Should we start again? Here what's cool. This is this button. It's called step backward. And you can press it. And you go back. You can go back in time to whatever point you need. Back, 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 back. And you go it's basically a time travel. So, and we can easily debug here. right? And probably we all know the exercise in binary search. It's always something about the inclusivity of the range. That's the most common issue. And to be honest, like there is this one. So if we debug, we see the values, and we say that this range should be inclusive, from left to right, inclusive right, including right point here. And this is actually the state that we are not getting into. So we have a left on 2, right on 2. And we will never actually go to this, the inclusive state here. So the correct answer is going to be like, okay, let's put like this. And voila, the issue fixed. So we have a pretty easy way to debug constant expressions, right? You may wonder, like, how do you run debugger in compile time? You can't run debugger in compile time. So let me jump into it a bit more. So first, before diving under the hood, let's ask the question: how does a compiler evaluate const expressions like GCC? How does it do it? Anyone know the answer? Okay, we have a few hands. So we have a quite experienced audience. So and the answer is something that's called CTFE. If I get it correctly, it's called like compile time function execution. Am I right, folks? Okay, probably something like that. Wikipedia says like this. And what basically it does, it takes sources of your like C++ program, it parses it, it creates an AST, like a data structure for storing code. It's an abbreviation for abstract syntax tree. Actually, how many of you know what AST is and like used it? Okay, good. Thank you so much. Like really nice that I don't need to explain it to everyone. Yeah, basically it's a representation of your code. So this is your code, right? This is a variable declaration. This is like a numeric literal and so on. And what we do, we store it in the like special types of trees, which are called abstract syntax trees. And it's just a data structure, like a regular tree that is like very easy to represent in the computer program and very easy to implement algorithms on. So it's just, you can think about it as a graph or as a tree and so on. And the algorithms are usually the same. It's depth first search, breadth first search, and so on. So back to our point. What the CTFE in the compiler does, it takes sources, it parses them, then we have abstract syntax tree, and then we go to the interesting part, which we start interpreting the AST with the data, and then we get the result, and then we store it somewhere and so on. The interesting part here is the AST. Well, actually, CLion is an IDE, and every feature in IDE is built upon those like abstract syntax trees. So we have like a lot of them. We have the tools to work with them. So we thought, okay, let's use it, right? The compilers use it. We can implement the same, right? And actually, that's basically what we did. So initial thinking was like that. We need to emulate something like a debugger, right? So the naive approach would be, okay, we can allow to set breakpoints, we can allow to run the AST interpreter until we hit the breakpoint, then we can inspect the state, then we can continue. And like the issue here is that usually in computer science there are like a few problems, right? It's like naming, off-one errors, and then managing the state. It's usually the most complex thing. And in the naive approach, we would have this iterative increment of the state, which is quite hard to do, because IDE is a very complex program. and a lot of moving parts here and there, a lot of shared memory, shared objects, and we don't want to get into the state management here in additional feature. Otherwise, it will break apart like very easily. So what we did was a bit like smarter in my sense. Instead of maintaining the state and re-evaluating it from scratch every time, what we actually did, we started evaluating it and rerunning and keeping the track of the commands that user is inputting to the IDE. So how it looks? Basically, under the hood, we have something like we call it command list, right? When the user presses, like, go to the step into the debugger or step over, what we do is we just populate this list. So let's imagine there's a user action, right? And when we start debugging, the command list is empty, of course. When we step into, we write step into the command list. What we do next? Next, we execute the, we take the AST, we take the chain of commands, and we execute it. And we get the result, and we store the result basically here. You can see it like this, right? This is the result. We don't manage any point of the state here. And what we do next? Let's imagine we user like asks to move one step forward, and they input like, okay, let's move to the next step. What we do? We just put to the command once again. Then what we do? We start all over from scratch, from the 0 point, from this basically from this point. We just execute it all over again. Just we do the right number of commands. We get this with the result. We print it out, and we show it to user. Step over is the same. Nothing interesting. You all know the drill right now. And there is actually a question for you. I showed the step back feature that we can go backwards. Anyone wants to take a guess how it's implemented, given that we are operating on the command list here? Anyone? I think you. Yes, but that's correct answer. So basically what we do when we ask step backward is we take the command list and we just pop the last state from it and re-execute all over again. So it's really you know this there's this principle, it's called KISS, keep it simple stupid, right? US Navy in the 60s was pretty decent by promoting it, and it's really simple, and we don't have to deal with the complexity of managing the state. We don't do like any real hard work. We just use the AST. We use the abstract syntax tree interpreter, and we just execute the commands, and that's it. I wonder when Microsoft will copy this feature. Let's hope we have a few more years. So, and why on earth does this work? So first of all, constexpr is deterministic. We don't have the UB here, so it's easier and so on. Second, no input-output, no global state, no issues. And actually, re-evaluation is pretty fast. We say that it's n steps per evaluation. So basically, for your debug sessions, you do the quadratic number of steps. So it's n to the power of 2. So pretty decent. It's much faster than parsing. It's super fast. And actually, as a mental model, you can think about of it like of a pure function. You can call it again and get the same answer. It's just a function that depends on data, and in our case, data is just a command list and the abstract syntax tree. So with the same abstract syntax tree, with the same command list, you get the same answer. So pretty easy, pretty elegant solution here. What's not supported yet? So unfortunately, we don't support dynamic allocations at the moment. So all those nice things from C++ 20 with vectors and new and deletes and so on are not working. It's not a big issue. We'll probably resolve it in the next releases. And the not very good thing is that we don't have breakpoints right now. So what I've showed you is like to start it all over again from scratch and to just step into like every time, which is a bit tedious for developers. And we actually want to, of course, to set the breakpoint and then to execute it and then run to the breakpoint. Unfortunately, this doesn't work right now, but it's pretty obvious how to fix. We know the placement of the breakpoint. We just populate the command list as we did previously, just automatically, and so on. And the thing is, you may ask, okay, what do we do in this case? So for example, let's say we have another constexpr function, which is like foo, of course. What we do here is, no, we don't return 42. Let's not forget to, then we do for, no, we are not doing j. We are doing something like this. And we return I here. And let's call it here. So you may ask, what do we actually do if we want to step over this function call? Let's take an example. So for example, what we do. If we step over, there's no magic. We still iterate the same amount of time. So it's nothing like really magical here. It's just like interpretation of the abstract syntax trees. You just go to another files, you take the syntax tree and you iterate, and so on. So it's like really, really simple. Okay, so that's about the limitations. So what are the takeaways here? So first of all, congrats, constexpr is now debuggable. It's not like 100% debuggable because of the limitations, but we are getting there. Give us more time. You will be able to debug everything. It's just an AST interpreter. No magic, no nothing. Like pretty simple. We don't manage like incremental state updates, no nothing. Because just imagine if you try to optimize the runtime and do it like just linear, not square, just imagine how hard would it be to go backwards if we keep the state. So let's say we increment, we do +1 step, and then we go -1. No, it's not going to work. Only in runtime when you have the memory that you can capture and memory snapshots, like I think undo does it, and you can do like real-time travel debugger. But we don't have memory here, so it's very simple, no magic. And guess what? Simplicity is good, right? Yeah, I think that's the main point. So a bit of promo. Download CLion 25.3. It's actually free for non-commercial use. So just play around with this debugger. Give us feedback because we want to improve it like further. And we actually believe that the feature is pretty useful in real life. You can reach me out on email. You can reach me out on LinkedIn. You can do this. If you are not happy with CLion, you can go to help, and then you what do you do? You contact support or submit a bug report or submit feedback. Okay, yeah, you complain, and we'll get your complaints there. You can also say Artemy asked to complain, so you can leverage it as well. Try to resolve your issues faster. So thank you so much, MUC C++. Thank you so much, BMW, for hosting us. Thank you so much for the organizers, and thank you so much for coming. Before we jump to the questions, I have my beautiful team here. Marie is here, Daniel, and Dmitry. If you are going to ask very hard questions, we will, as a manager, I will delegate those questions. They didn't have a chance to run to the bathroom break, so I put them on the spotlight. So thank you so much, folks. Your questions. Oh, interesting. Yeah, of course. Mike.
Test. Hello. Oh, yeah, now it works. Yeah, so you were kind of baiting me with that example of jumping over the foo function with the loop. What if instead of looping to 10, you loop to int max in that function? What happens if you try to step over it?
I know it was coming. Let's try. So, say when it's enough.
Yeah, something like that. Well, it should still fit in an int, but yeah.
Okay, that's interesting. It's overflow. Let's do it like that. Let's do the long here. We can't use longs. So probably even the compiler doesn't want to do more. So we have, as usual, hard limits probably. And in our code, we have a limit for, I think, 250,000 calls, something like that. So probably it's on the same par, with the compiler.
Okay. Yeah, that's very reasonable.
Okay.
Thanks. I was just hoping it wouldn't crash the IDE, but it doesn't.
So there is a question.
Hello, thank you very much for the talk. Who built the executor? Have you built this executor, or is this coming from compiler?
We built it ourselves. And you may ask, okay, like, why I'm saying this about explicitly CLion 25.3 is because in this release we actually changed the C++ language support engine. So what we did, we actually have a separate process right now that is running like C++ engine support, is parsing, inspections, and so on. And this thing is also implemented in this new engine. So that's why it's available only then. Yeah, and we implemented it ourselves, so it's basically from scratch. And we implemented it in C#. And actually, JetBrains is usually a Java Kotlin company. And we are making a C++ IDE, and we implemented it in C#. Don't ask me why. Yeah. So it's we built it ourselves, yeah.
Okay, thank you very much.
A very long answer for a very short question. Sorry.
Here. I would have here on the...
Oh, okay.
First of all, thanks a lot. I mean, I think this constexpr, it's always a challenge. But now that you achieve it, the C++ committee give you something to not get bored.
did you start thinking about reflection and how we'll debug that?
Let's ask our engineers. Daniel, do you want to support reflection there? Oh, okay. So there are some commits about it. No commitments, no guarantees, but there are some commits in Git history.
Thanks.
I think first we need to deal with the dynamic allocation, actually. There is a mic somewhere already. Yeah.
It's interesting you built your own execution environment for the const expressions, but I'm a bit surprised to hear that you're directly interpreting the AST. In an AST, identifiers are just strings. They don't have a scope and they don't have any types. What the Rust compiler does is that it first transforms the AST into a mid-level intermediate representation.
Yeah.
So each variable would be an ID that belongs to a certain scope and has a certain type. So how does this work for you engineering-wise?
So what we do is at JetBrains we have this like our version of AST. It's not just an AST that is written in the books or in the compilers. We call it actually PSI tree, program structure index tree, and those are basically like objects. In like the tree is represented like as a complex set of complex objects with a relation to each other, and those can store types. Those can try to evaluate themselves. Those can have references to other elements. So basically, it's not like a tree, to be honest. It's more of a forest or something like that. Yeah, of course. So it's to answer your question, we are using like a more complex version of an AST. So that's why we don't need like a direct IR as it done in Rust.
That explains it. Thank you.
Yeah. That's the question.
First of all, thank you for developing this. Would have saved me a massive headache about a year ago. On the topic of wanting always more, are there thoughts of also creating a profiler for constexpers?
Oh no, not right now. What you can do, go to help, submit feedback, or contact support and ask our support team, and then we will show to our engineers, and they will say no, and then we will, when we get more and more votes on the ticket, then we probably implement it.
All right, noted.
Yeah. So any other questions? Okay. Oh, okay, there's their hand.
So how many votes did this feature get? Or were there many people who wanted this, or is it just you wanted it?
I think it happened during a hackathon. So what we did when we were migrating to the new like C++ language support engine, we had this AST interpreter already built in, because we needed to do those kind of, let me create a bug back. So we have the red highlighting here. You see like this. Something comes from clangd, and something comes from the our support as well, and we can evaluate some stuff and put them into inspections and highlighting as well. And our thinking was, okay, we have this cool technical feature, technical ability. Let's try to featureize it into something useful. And during hackathon, folks implemented it, and basically we took it live this year. I think it was implemented a year ago, actually, like initial prototype of this feature. Yeah, and actually, surprisingly, we have a pretty good adoption of this. Even though the amount of C++ up to like C++ 17 and C++ 20 is not like that high in our stats, we see that like quite a lot of people already try this feature and use it quite often.
Yeah. Thank you.
Hope you join us in using the feature.
Hi.
Yeah. Hey.
Just a quick question. So I understand that you're probably not using a VM to execute constexprs, but I imagine you must have some virtual memory or something to keep the state when dealing with like statically allocated things.
Yeah, so we have a, I think it's called something context that is being passed to the. I showed this the execution phase. So we basically have this function. It takes not only command list and AST, it also takes like an empty context object, and it gets populated as we execute. The thing is, we just use it once and then delete it fully, just to not bear ourselves into the n+1 step, like after the keeping it for a long time in the view. And so it's also a bit difficult because we have right now there are two processes running. One is that C# based new C++ engine. It's in a separate process. The UI of the IDE is in a separate process, and like passing states, synchronizing states between them, it's like usually not a great idea. It adds complexity. Yeah, so that's why we. To answer your question, yes, we have some context object that we populate when we go to the execution, but we don't keep it for a long time. We just delete it as soon as it's done.
Thank you.
Before executing, do you do any kind of optimization on the AST, or how do you approach that?
Well, we can just use the bare AST that we have inside. We like try to keep it simple, so we try not to over-optimize before we really have to optimize something. Sometimes it brings some issues because you can like say, okay, ID is lagging again, and we solve it more often than not. And yeah, and this actually engine optimization and this separation of processes was brought in by us when we saw that okay, a lot of people are experiencing lags, and by separating something into two processes, we don't have to block the UI thread. So it was very useful thing. Like out of it, we got the new engine, we got new features. We got this constexpr debugger, and we got better performance in general. But to answer your question, like a simple question, no, we don't do any optimizations on the AST before the execution of constexpr debugger.
And doing execution, like storing sub-results or something?
Excuse me?
Like, do you so you said you are not doing anything before execution. Are you doing like optimization during execution, like storing?
No.
That's okay.
Could you shed some light on what the challenges are with dynamic allocation? Because typically when I'm debugging constexpr stuff, I care about when I have like containers and strings and stuff like that. So,
what's the issue with the
constexpr? What are the challenges with supporting dynamic allocation debugging?
We just didn't implement it yet. So
next release?
It's harder than implementing like the just variables, loops, and if statements. But it's this exercise like opening bracket, closing bracket, and so on. So I think it's on the same side of complexity, not very complex. We just need to do it Yeah. So there is an issue. You know the drill already. Help, contact support, and we will, with every more vote, we get closer to fixing the issue itself.
So one nice thing about constexpr is that if you write something that invokes undefined behavior, it doesn't continue executing, it results in a compile error. How does that work with your debugger? Like if I have undefined behavior in my constexpr execution, can I just run it and then it will stop at that point and I can step backward from where the undefined behavior happened? Or what's the experience there?
Oh, that's a good question. I didn't try it. Want to try? You can try it yourself, actually.
I mean, yeah, let's see if I can think of something that would, we can maybe try an uninitialized variable. Try have a function that tries to like return an uninitialized value or something.
Okay, so we have a variable, we don't initialize it. What we do with it? Try to access it, right? Somehow. Let's,
I++ and then try to return it. That should be enough.
oh, let's see how it goes. I actually need to return something. I don't know. Let's call it. Okay. So the inspection works. Well, let's run it. No, it's the after that it dies.
Okay, but can I step backward from that?
Yeah.
Yeah, that works. Oh, that's cool. Nice. Thanks.
If I recall correctly, there's like a limit on maximum recursion depth in the const expression execution in the compiler. How does your debugger deal with it?
We have some limits as well, like hard-coded basically. Nothing that it's something like max with like caps locked names, so you know, max limit for something.
Okay, but can the user like execute the recursion until the point where it reaches the maximum depth?
So you want to try it out? Or
Sure.
Okay. Let's call Fuber.
Maybe add like a def counter or something.
Yeah, so let's see. How it goes. So we are coming to 400. 400. Okay, so it was 700 something.
And you can step back, sadly.
Yeah, I think it's dead.
How easy would it be to expand this to other languages that have a similar notion of compiler time evaluated expressions?
As long as this language support has the same kind of interpreter that we do. So for example, Rust, right? Like I think Rust has the same thing. Yeah, we need to go to the Rust team and ask them, hey folks, I want to spend 2 months of your life to do it. And then, yeah, probably they will. You can, yeah, you know the drill, right? I think support engineers will not be happy with me after this talk.
Hi, hello. I was thinking of a few more advanced debugging features that might be missing, I guess. Like, it's nice when you can change the value of a variable while you execute, and then you can, like, I don't know, plant a different spotting code or like trigger different behaviors. Is that something that can be done with this engine?
Ah, so you mean the changing the value?
Yeah, like set I to 1 or something.
I think no. Let's try. What we can definitely do here is we can we can actually evaluate expressions. Okay, so sorry, we need to remove this one. The bad one. So what we can do is we can evaluate expressions. For example, we can write left, right plus target and get the result. Let's see if we can. I think we won't be able to do it because, as far as I remember, we don't store the change of variable event. Let's say 0 left is 10. I think on the next temp, yeah, so it's wiped out. So basically, if we want to do it, I think we can store the command of assigning left 10 in the same command list and then repeat it, play back.
Yeah, I mean, it looks doable, just asking if it was already implemented. I know the workflow to support. Also, I'll admit I'm more used to GDB than JetBrains, but one nice feature, I think, is also pretty printing complex classes, complex objects. Could that be done here somehow? Like if I have a complex class and I don't want to like look at, I don't know, individual bytes in a string, for example.
You don't believe me, but we have a debugger guru here with us. Dima, any comments on this?
Well, don't forget that this is a compile time. GDB doesn't work in compile time. So it's not like you can use GDB for this. I would say it would be pretty hard because like GDB pretty printers are in Python. So we have somehow to integrate Python interpreter into our C++ interpreter. I guess it would be non-trivial.
Fair enough, thanks.
Thank you. There is also a question in the middle. Yeah.
So constexprs can be evaluated at compile time. They can also not be. What happens then? So if I have a constexpr expression function that I'm calling at runtime, either because I pass the user input or because I pass it a parameter that is only evaluated at runtime, what kind of a debugging experience can I expect then?
So what you can expect here is here it's already showing this debug evaluation only in the compile time context basically. And in other cases, when it's not a compile time context, you won't see the debug icon. So basically, it will try to understand whether it's a compile time context or not, and then decide whether to show the icon or not. So in the runtime, you don't have this kind of debugger.
So we just have the normal.
Yeah.
Okay. Thank you.
Oh, there's a hand. Okay.
Do you have an example for, I believe in the beginning you said that sometimes evaluating a const expression at compile time differs from evaluating it at runtime, which is why you recommended against the commenting out constexpr and then just stepping through it with the normal debugger.
Okay. I think I will play my I used C++ decently 10 years ago card.
Okay.
Here, sorry. Yeah. No answer. Daniel?
Yeah, I mean, if you have if constexpr code, then you get different evaluation branches depending on how you call the function.
I actually don't know C++ well enough for that. I'll just pretend I understand.
Okay. Any other questions? Okay, then I think that's it. Thank you so much, folks. It was a pleasure. Let's chat, let's eat, let's drink. Thank you so much.